SOP circuits can be realized with minimum NAND gates, whereas the POS circuits can be realized with minimum NOR gates. These things I already told you. The sum of product circuits can be realized with a minimum number of NAND gates, whereas POS circuits can be realized with a minimum number of NOR gates. So this is an important point that you always have to keep in your mind. The sum of product terms can be realized with a minimum number of NAND gates, whereas POS circuits can be realized with a minimum number of NOR gates. Here I have already told you n bit into n bit. So if you do the multiplication of n bit and n bit in the binary format, so whatever the resultant bit that you are going to get, which is n plus n number of bits. So here, suppose if now I am going to the binary multiplication. Suppose I am going to do the binary multiplication, you can see clearly. So this first digit has the n number of binary bits and the second digit is having a n number of binary bits. So if you do the multiplication of these two binary bits, whatever the resultant binary bit will have the n plus n number of bits. So we can say this is the first digit of binary, it has n bits, and the second digit of binary is has n bits. So if we do the multiplication of these two binary bits, we are going to get a resultant binary bits of having a bits of n plus n. So the first binary number has a n bits and the second binary number has a bits of n. So if you do the multiplication of these two binary bits, then you are going to get the overall binary of number of digits, the number of places of n plus n. So therefore n bit binary into n bit binary is equal to n plus n of binary. So we can say basically, suppose this is a binary number having n bits, this is also binary number having n bits. So if we do the multiplication of these two things, we are going to get resultant binary of number of bits of n plus n. And the rate of addition is the number of complete additions in 1 second. So rate of addition means the total number of additions which are taken place in 1 second is called as the rate of addition. I already told you the rate of addition of the number of complete additions in 1 second is equal to 1 by time delay, or we can say time taken for one complete addition, which is 1 by which is a t. We can say basically the n minus 1 into TPD carry plus maximum value of TPD sum or TPD carry. These things I have already told you. So rate of addition means the total number of additions that are taken place in 1 second is called as the rate of addition. So basically the rate of addition means the total number of additions which are taken place in 1 second. This point I have already told you, which is combining cells in the 2 to the power of n so that n variables are redundant. I have already told you, suppose if you are going to combine the cells of 2 to the power of n, then n number of variables are redundant. So it means these variables you are going to lose them. So therefore, if you basically group the cells in the power of 2 to the power of n, then n variables are redundant from the overall expression. So we can say basically combining cells in the 2 to the power of n so that n variables are redundant. So if you are grouping the cells in the order of 2 to the power of n, then n number of variables are redundant. So if you are going to combine the cells in the 2 to the power of n, so therefore if you are combining the cells in the order of 2 to the power of n, so that the n variables have been redundant. So if you are combining the cells in the order of 2 to the power of n, then 2 to the power of n, then n variables have been redundant from the expression. So if you are going to combine the cells in the power of 2 to the power of n, so that the n variables have been redundant. These things I have already told you. Always you have to group from higher group cells to the lower group cells. So for n variable in K-map, maximum possible essential prime implicants are 2 to the power of n minus 1. I have already told you this important point. See, for n variable, you are going to get 2 to the power of n minus 1 terms are always 1. Always 1 for which one? XOR gate or XNOR gate. I have already told you. So therefore, for n variable, always you are going to get 2 to the power of n minus 1 number of ones for a XOR gate. So these ones definitely we are going to get. So therefore, the maximum possible essential prime implicants are 2 to the power of n minus 1. So therefore, this is something that you always have to keep in your mind. So for a n variable in K-map, the maximum possible essential prime implicants are equal to number of ones in a XOR gate or we can say XNOR gate. So always it is equal to 2 to the power of n minus 1. So therefore, simply we can say for a n variable in K-map, the maximum possible essential prime implicants are 2 to the power of n minus 1. So for a n variable in K-map, the maximum possible essential prime implicants are 2 to the power of n minus 1. So for a n variable in K map, the maximum number of essential prime implicants are 2 to the power of n minus 1, because I already told you for a n variable, you are see for a XOR gate, the number of ones are nothing but it is equal to essential prime implicants, which are 2 to the power of n minus 1 ones are going to present. So these may number of essential prime implicants are going to get present. So finally we can say for a n variable in K map, the maximum possible essential prime implicants are 2 to the power of n minus 1. The number of 2 cross 1 mux needed to implement the 2 to the power of n cross 1 mux is equal to 2 to the power of n down minus 1. And what I told you, the number of 2 cross 1 mux needed to implement the 2 to the power of n cross 1 mux is equal to 2 to the power of n down is minus 1. So therefore, say 2 to the power of n minus 1 number of mux of 2 cross 1 mux are needed to implement the 2 to the power of n cross 1 mux. So therefore, the number of 2 cross 1 mux needed to implement the number of 2 cross 1 mux needed to implement the 2 to the power of n cross 1 mux is equal to 2 to the power of n minus 1. So therefore, the number of 2 cross 1 mux needed to implement the 2 to the power of n cross 1 mux is equal to 2 to the power of n minus 1. So therefore, simply the number of 2 cross 1 mux needed to implement the 2 to the power of n cross 1 mux is nothing but 2 to the power of n minus 1. So this is a point that you always have to keep in mind. So therefore, the number of 2 cross 1 mux needed to implement 2 to the power of n cross 1 mux is equal to 2 to the power of n minus 1. So simply we can say that the number of 2 cross 1 mux needed to implement the 2 to the power of n cross 1 mux is equal to 2 to the power of n minus 1. So therefore, 2 to the power of n minus 1 number of 2 cross 1 mux are needed to implement the 2 to the power of n cross 1 mux. These things I have already explained. So therefore, the implementation of higher order demux using lower order demux is just the mirror image of the mux implementation. Yes, I already told you whatever the demux is the mirror image of the mux. So therefore, whatever the demux is nothing but mirror image of the mux. So therefore, the implementation of higher order demux using the lower order demux is just the mirror image of the mux implementation. So therefore, if you want to see, basically if you want to build the higher order demux in terms of lower order demux, you have to just follow the procedure of the mux, but only thing it is a reverse point, it is a mirror image of the mux. So we can say that, see, if you want to implement the higher order demux using the lower order demux, then whatever this procedure is same as the mux procedure, but only thing is it is a mirror image of the mux. So therefore, the implementation of higher order demux using the lower order demux is just the mirror image of the mux implementation. So we can say the implementation of higher order demux using the lower order demux is just the mirror image of the mux implementation. These things also I already explained. So therefore, whatever the implementation of the higher order demux with the help of lower order demux is nothing but it's a mirror image of the mux implementation. So therefore, the implementation of higher order demux using the lower order demux is just the mirror image of the mux implementation. So therefore, the implementation of the higher order demux using the lower order demux is just the mirror image of the mux implementation. So therefore, the implementation of the higher order demux using the lower order demux is just the mirror image of the mux implementation. The implementation of decoder is same as demux. I have already told you decoder and demux are same. Just thing is we are interchanging the enable and the select lines. So if we interchange the we can say enable and select lines of demux, we are going to get the decoder. So therefore, both are identical. So whatever the implementation of decoder is same as the implementation of demux. So this is the point that you always have to keep in your mind, because decoder and demux are same. Just we are interchanging the enable and the select lines, then we are going to get the decoder from the demux. Therefore, whatever the implementation of decoder is same as the demux. See, if one input is equal to 0 and in respect of other input, output is always equal to 1 for NAND gate. I only told you here for NAND gate, if one of the input is equal to 0, irrespective of the other input, always the overall output of NAND gate is always equal to 1. So therefore I already told you for NAND gate if one of the input is equal to 0, irrespective of the other input, always the output of the NAND gate is always equal to 1. So therefore if one input is equal to 0 and irrespective of the other input, output is always equal to 1 for NAND gate. So this point I already told you. So therefore if one of the input is equal to 0, if one of the input is equal to 0 and irrespective of the other input, always the whole output of the NAND gate is always equal to 0. So therefore is always equal to 1. So therefore if one of the input is equal to 0 and irrespective of the other input for NAND gate, the overall output is always equal to 1. So if one input is equal to 0 and irrespective of the other input, output is always equal to 1 for NAND gate. So next one is after invalid state, if you give 0, 0 input, the output Q bar can be 0, 1 or 1, 0. I have already told you this important point. Say after the invalid statements for SR flip-flop, if you go 1, 1, we are going to get invalid statements. Both are Q and Q bar having the same output. We are going to get the same output. So what I am going to do now basically, suppose after this state, if I give 0, 0, it is a memory. When S is equal to 0 and R is equal to 0, we are going to get the memory. But now the output should be memory, the previous state, but it will never be the previous state. It will be either 0, 1 or 1, 0 based on whichever the device is acting very fast. Or we can say having the less propagation below. So therefore simply we can say after invalid state, if you give 0, 0 input, the output Q bar can be either 0, bar or 1, 0. So because of this reason only, we can't predict the output. So therefore because of this reason only, we are not going to use the S is equal to 1 and R is equal to 1 because it is going to give you an invalid state. So this is the basic agenda of this one. So therefore after invalid state, if you give 0, 0 input, the output can be either 0, 1 or 1, 0. So because of this reason only, we can't predict the accurate answer. It is depending upon the speed of response of the we can say circuits of the NAND gates or NAND gates presenting that SR flip-flop. So therefore output is going to get changed. So because of this reason only, we are not going to use the invalid state. So after invalid state, if you do 0, 0 input, the output Q bar can be 0, 1 or 1, 0. The next point is if one input is equal to 1 and irrespective of the other input, output is always equal to 0 for NOR gate. I have already told you for a NOR gate, if one of the input is 1, irrespective of the other input, always the output is equal to 0 for a NOR gate. These things I have already told you. For a NOR gate, if one of the input is 1, irrespective of the other input, always the overall output is nothing but 0. So therefore for NOR gate, irrespective if one of the input is 1, irrespective of the other input, always the output of the NOR gate is always equal to 0. These things I have already told you. So if one input is equal to 1 and irrespective of other input, output is always equal to 0 for NOR gate. Say I have already told you an OR function means output of XOR gate. Say an OR function means output of XOR gate. I have already told you XOR both are same. XOR or XOR both are same. See only for odd number of inputs the output is always equal to 1. That is the meaning of OR function. So therefore OR function means for odd number of value of input ones only the output is equal to 1 and for remaining cases it is 0. So that is the meaning of the OR function. So OR function means for odd number of ones only the output is equal to 1 and for remaining cases it is going to become 0. So that is the reason it is called as the OR function. So simply we can say XOR gate or XOR gate is called as an OR function. So an OR function means output of XOR gate because only for odd number of input values of 1 only we are going to get the output is equal to 1 and for remaining cases we are going to get 0. So because of this only XOR gate or XOR gate is called as the OR function. See whenever the present output is equal to function of present input, it is called as a combinational circuit. I have already told you in a combination circuit the present output is going to depend only on the present input, or simply we can say the present output is a function of only present input for a combinational circuit. So therefore this is the meaning of this one. So therefore we can say simply for a combination circuit the present output is always a function of present input only. So there is no feedback in the combination circuits from output to input. Whereas in the sequential circuits, the present output is a function of the present input and also the past output. So this is called as a sequential circuit. So therefore there is a feedback here. So whenever the present output is a function of the present input and also the past output, it is called as a sequential circuit. So this is a point that you always have to keep in your mind. So therefore, whenever the present output is a function of only present input, it is called as a combination circuit, and there is no feedback in the combination circuit. And whenever the present output is a function of the present input and the past output, then it is said to be a sequential circuit, and there is always a feedback in this sequential circuit. So these are the points that you always have to keep in your mind. So for a combination circuit, always the present output is a function of only present input and there is no feedback, whereas in the sequential circuit, the present output is a function of both the present input and also the past output, and there is a feedback in the sequential circuit. So these things that you always have to keep in your mind. So now you can see clearly here. So basically, if you want to convert the analog input to digital output, we have to keep a ADC. ADC is nothing but it is basically analog digital converter. So whatever the analog input, we are going to convert into digital input, and here we are going to keep the digital system because it is going to process only the digital input and it is always going to give you the digital output. But we want to see in the terms of analog, so we have to keep here digital to analog converter. So whatever the output, we are going to get the analog, because human can only understand the analog input or analog output, but it never understands the binary. So because of this only, we have to keep the ADC in front of the digital system and DAC after the digital system. So therefore, in the input side, we have to keep the ADC to convert the analog input to binary output, and this digital system is going to process this binary data and is going to give you a binary output. And here we have to keep the DAC, digital to analog converter, so we are going to get the analog output. So this is so we can exercise that we always have to keep in our mind. Here we are going to use the ADC and here we are going to use the DAC. So therefore, here analog input is, so with the input of analog digital converter, we are going to convert the analog input to digital output, and this digital output is being processed, and this digital input is being processed by this digital system and is going to give you digital output. And here we have to keep the again DAC, digital to analog converter, so therefore it is going to convert the digital to analog. So human can understand only the analog nature but not the digital nature, but the digital systems are going to understand only the digital data but, or binary data but not the analog data. So because of these reasons only, we have to use the ADC and also DAC. So I have already told you A plus BC is equal to A plus B into A plus C. I have already told you this is called as the distribution theorem. So therefore A plus BC is equal to A plus B into A plus C. So in this simplification, A into A is equal to A and A into C plus B into A plus B into C. So if we do simplification, finally we are going to get A plus BC is equal to A plus B into A plus C. It is called as the distribution theorem. It is called as the A plus BC is equal to A plus B into A plus C. It is called as the distribution theorem. So always this bracket has more priority than the NOT gate, and NOT gate has more priority than the AND gate, and AND gate has more priority than the OR gate. So the way this we can say precedence order in the logical minimization. So always we have to go for whatever the data present in this bracket has the highest priority, then comes the NOT, then comes the AND, then comes the OR. So we can say this is the precedence order in the logical minimization. So this is the order that you have to follow in order to do the logical minimization of any complex expression. So this is the order that you always have to go in order to do the simplification of any larger canonical expression. So therefore always whatever the data present in the bracket should be minimized first, and then below the NOT gate you have to say next, and then with the AND then you have to go for the OR. So this is the thing that you always have to keep in your mind. So bracket, next comes the NOT, then comes the AND, then comes the OR. So this is the order that you always have to keep in your mind. So this is the order that you should always follow if you want to do the minimize of any complex expression. So therefore simply we can say that the bracket has the more priority than compared to NOT, and NOT gate has the more priority than the AND gate has more priority than the OR. So this is called as the precedence order in the logical minimization. So this is the precedence order in the logical minimization, means this is the order that you should always follow in order to do the minimization of any complex Boolean expression. I have already told you AB plus A bar C plus BC is equal to AB plus A bar C only. So this is called as the consensus theorem. So this is called as the consensus theorem. So AB plus A bar C is plus BC is equal to AB plus A bar C. I already told you this theorem is called as the consensus theorem. So therefore AB plus A bar C plus BC is equal to AB plus A bar C. It is called as the consensus theorem. So AB plus A bar C plus BC is equal to AB plus A bar C. It is called as the consensus theorem. So AB plus A bar C plus BC is equal to, it is called as the AB plus A bar C. It is called as the consensus theorem. So AB plus A bar C plus BC is equal to AB plus A bar C. It is called as the consensus theorem. So AB plus A bar C plus BC is equal to AB plus A bar C. It is called as the consensus theorem. So AB plus A bar C plus BC is equal to AB plus A bar C. It is always called as the consensus theorem. So if you see clearly, here there is A, here there is A bar, here there is B, and here it is C. So now you have to the product of these two things. So BC, then whatever this overall is called as the AB plus A bar C, it is called as the consensus theorem. So AB plus A bar C plus BC is equal to AB plus A bar C. It is called as the consensus theorem. So therefore AB plus A bar C plus BC is equal to AB plus A bar C. It is called as the consensus theorem. The duality expressions on any valid expression is also a valid expression. I have already told you, if you apply the duality principle on any valid expression, then whatever the resultant expression is also a valid expression. So therefore, if you apply any duality expression, if you apply the duality property on any valid expression, then whatever the resultant expression is also a valid expression. So this is the important point that you always have to keep in your mind. So the duality expression on any valid expression is also a valid expression. So therefore, if you apply the duality principle on any valid expression, so whatever the resultant expression is also a valid expression. So therefore, I already told you, if you want to do the duality, then you should not change A, then you should not change A bar, but you have to change AND to or to and we can say 0 to 1 and 1 to 0. These things I already told you. So if you apply the duality expression, if you apply the duality principle on any valid expression, then whatever the resultant expression is also a valid expression. So this point that you always have to keep in your mind. Or the switch is equal to 0 means it is off, and whenever the switch is equal to 1 means it is on. Similarly, whenever the bulb is equal to off means it is 0, and whenever the bulb is equal to on means it is 1. So this is a very simple thing that you always can easily understand. So whenever the switch is equal to 0 means it is in the off position, and whenever the switch is equal to 1 means it is in the on condition. Similarly, whenever the bulb is equal to off means it is 0 condition, and whenever the bulb is equal to on means it is in the 1 state. So in terms of binary, so we are writing the off and on state in the terms of binary. So off means 0, on means 1. So for staircase switch in electrical circuit is equivalent to XOR gate or XNOR gate depending upon the connections. So therefore simply we can say for a staircase connection of switch in electrical circuit, it is equivalent to either the XOR gate or XNOR gate depending upon the connections. So this is an important point that you always have to keep in your mind. So for staircase applications, whatever the switch is there, the switch connections in electrical circuit is equivalent to XOR gate or the XNOR gate depending upon the connection. So this is an important point that you always have to keep in your mind. So therefore, for staircase applications, whatever the switch in the electrical circuit, it is equivalent to XOR gate or XNOR gate depending upon the connections. So for staircase applications, whatever the switch in the electrical circuit is equivalent to XOR gate or XNOR gate depending upon the connections. So for the staircase applications, whatever the switch configuration, it is in the electrical circuit, it is equivalent to XOR gate or XNOR gate depending upon the connections. So dual expression is used to convert the positive logic to negative logic and vice versa. I already told you, basically the meaning of duality is we are going to convert the, we can say, positive logic circuit to negative logic circuit, similarly from negative logic circuit to positive logic circuit. These things I have already told you. In the positive logic circuit, we can say high voltage is called as the logic 1 and low voltage is called as the logic 0. Whereas in the negative logic, high voltage is logic 0 and low voltage is logic 1. These things also I have already told you. So therefore, the basic agenda of the duality is to convert the positive logic system to the negative logic expression, and similarly negative logic expression to the positive logic expression. So this is a point that you always have to keep in your mind. So therefore, the dual expressions are used to convert the positive logic to negative logic and negative logic to the positive logic. It is the vice versa. And similarly, I have already told you the NOT gate, AND gate and OR gate are called as the basic gates. See, AND gate and NOT gate, AND gate and OR gate are always called as the basic gates. Whereas the NAND gate or NOR gate is also called as the universal gates, whereas the XOR and XNOR are called as the derived gates. So these things that you always have to keep in your mind. So NOT gate, AND gate, OR gate are always called as the, which is called as the basic gates, whereas the NAND gate and NOR gate are called as the universal gates, whereas the XOR and XNOR are called as the derived gates. See, NAND gate and NOR gate are called as universal gates because with the help of NAND gate we can realize any of the gates, and with the help of NOR gate alone we can realize any of the gates. So because of this reason only we can call the NAND gate and NOR gate as the universal gates. And also MUX is also one type of universal gate. So finally we can say NOT gate, AND gate and OR gate is always called as the basic gates, whereas the NAND gate and NOR gate are called as the universal gates, whereas the XOR and XNOR are called as the derived gates. So these things that you always have to keep in your mind for all your lifetime. See, 1 picosecond means 10 to the power of minus 12 seconds. 1 picosecond means 10 to the power of minus 12 seconds, and 1 gigahertz means 10 to the power of 9 hertz, and 1 kilo is nothing but 1024. So these are the important things that you always have to keep in your mind for all your lifetime. So therefore, 1 picosecond means 10 to the power of minus 12 seconds, 1 gigahertz means 10 to the power of 9 hertz, and 1 k is nothing but 1024. So these are the points that you always have to keep in your mind. So 1 picosecond means 10 to the power of minus 12 seconds, 1 gigahertz means 10 to the power of 1 gigahertz means 10 to the power of 9 hertz, and 1 kilo is equal to 1024. 1 k is nothing but 1024. So 1 picosecond means 10 to the power of minus 12 seconds, 1 gigahertz means 10 to the power of 9 hertz, and 1 k is nothing but 1024. See, by using the duality principle twisely, we can minimize any Boolean expression. So therefore, here basically by using the duality principle twisely, we can minimize any Boolean expression. So therefore, simply we can say that by using the duality principle, twisely, we can minimize any Boolean expression. So therefore, simply we can say that, see, we can use the duality principle even to minimize any Boolean expression twice. So therefore, sometimes the given expression may be very hard to solve it one. So go for the duality, do the simplification, and then convert again back to the duality. So you are going to get the original expression in a simplified format. So therefore, suppose there is a given expression, it's a very complex one. So try to do the one duality. So therefore, if you do some duality, you are going to get some expression. Again, do the duality of that one. After that, you are going to get the simplified result of the original equation. So therefore, we can say by using the duality principle twisely, we can minimize any Boolean expression, because f to the power of duality is equal to function itself. So that is the reason we have to use the duality principle twisely. So therefore, we can minimize any Boolean expression. So therefore, by using the duality principle twisely, we can minimize any Boolean expression. See, a bar b and a bar plus b and a bar and a plus b bar are also called as the universal gates. So these are also very important points that you always have to keep in your mind. See, a bar b and a into b bar and a bar plus b and a plus b bar, always these are said to be universal gates. So a bar b and a b bar and a bar plus b and a plus b bar, always these are also said to be a universal gates. So these are the important points that you always have to keep in your mind. So a bar b and a b bar and a bar plus b and a plus b bar, these are always said to be a universal gates. So therefore, here a bar b and a b bar, similarly a bar plus b and a plus b bar, always these are always called as the universal gates. See, NAND gate and NOR gates follow the commutative law but not associative law. I already told you, whereas all the basic gates, NOT gate, NAND gate, NOR gate, see NAND gate, See, all the basic gates like NOT gate, AND gate, OR gate are going to satisfy both the associative and the cumulative property, whereas universal gates satisfy only the cumulative property but not the associative property. This property, this principle I have already told you in the given expression in the starting class only. So therefore, simply we can say that NAND gate and NOR gates, these are the universal gates, they only satisfy the cumulative law but not the associative law. So therefore, NAND gates and NOR gates follows only the cumulative law but not the associative law, whereas the basic gates follow both the cumulative law and also they satisfy both the cumulative law and also the which is called the associative law. See, unused input in AND gates is connected to logic 1 because always whatever the unused input in logic gates of the AND gate, so whatever the unused input in AND gate, you should always connect to logic 1. Similarly, unused input in OR gate is always connected to logic 0. So because unused input in OR gate is always connected to logic 0, whereas unused input in AND gate is always connected to logic 1. Similarly, unused input in OR gate is always connected to logic 0. So these things that you always have to keep in your mind. So therefore, simply the unused input in AND gate is always connected to logic 1. Similarly, the unused input in OR gate is always connected to 0, logic 0, whereas the unused input in the NAND gate is always connected to logic 1. Similarly, the unused input in the NOR gate is again connected to logic 0. These things that we can easily understand. So therefore, simply I can tell you that whatever the unused input in the AND gate should be always connected to logic 1, and whatever the unused input in the OR gate is connected to logic 0, and similarly whatever the unused input in the NAND gate is connected to logic 1, and whatever the unused input in the NOR gate is always connected to logic 0. These things that you always have to keep in your mind. See, OR gate is also called as the inclusive OR gate. So OR gate is also called as the inclusive OR gate. So whatever the OR gate, it is also called as the inclusive OR gate. So OR gate is also called as the inclusive OR gate. So whatever the OR gate, it is also called as the inclusive OR gate. So OR gate is also called as the inclusive OR gate. So this is a very important definition that you always have to keep in your mind. So therefore, OR gate is also called as the inclusive OR gate. So OR gate is also called as the inclusive OR gate. So OR gate is also called as the inclusive OR gate. So OR gate is also called as the inclusive OR gate. So these things that you always have to keep in mind. See, A XOR B XOR AB is always equal to A plus B. See, A XOR B XOR A into B is always equal to A plus B. See, you can easily simplify this expression and you will get the same result. It is equal to A plus B. So finally, A XOR B XOR A into B is always equal to A plus B. So A XOR B XOR of A into B is always equal to A plus B. See, XOR logic gate is also called as the coincidence or equality deduction or equivalence logic circuit. So whatever the XOR logic gate is also called as the coincidence or the equality deduction or equivalence logic circuit, because for a 2-input XOR gate, I already told you, whenever you are going to get the even number of ones, then you are going to get the logic as 1, and whenever in the reverse process you are going to get 0. So therefore, whenever the inputs are even number of ones in the XOR, you are going to get the logic as 1. So whenever the both inputs are equal, 0 0 means you are going to get 1, and 1 1 means again you are going to get 1. So for 2-input XOR gate, whenever both the inputs are equal, you are going to get the logic 1, whereas in the remaining cases you are going to get the logic as 0. These things that you can easily visualize from the XOR gate logic circuit itself. So XOR logic gate is also called as the coincidence or equal deduction or equivalence logic circuit. So therefore, XOR logic gate is also called as the coincidence or equal deduction or the equivalence logic circuit, because whenever both the inputs are equal, then only you are going to get the output as 1, whereas you are going to get the output as 0. So therefore, XOR logic gate is also called as the coincidence or the equal deduction or the equivalence logic circuit. So A bar B, A B bar are called as the inhibitor expressions, whereas A bar plus B and A plus B bar are called as the implication expressions. So these are the things that you always have to keep in your mind. I already told you all these are going to act like universal gates also. So therefore, A bar B, A B bar and A bar plus B and A plus B bar. All these are said to be universal gates, whereas A bar B and A B bar are called as the inhibitor expressions, whereas A bar plus B and A plus B bar are called as the implication expressions. So these things that you always have to keep in your mind. So A bar B and A B bar are called as the inhibitor expressions. So these are called as the inhibitor expressions, whereas A bar plus B and A plus B bar are called as the implication expressions. So A bar B and A B bar are called as the inhibitor expressions, whereas A bar plus B and A plus B bar are called as the implications expressions. So these things that you always have to keep in your mind. So A bar B and A B bar are called as the inhibitor expressions, whereas A bar plus B and A plus B bar are called as the implication expressions. Two-level AND or logic circuit is equivalent to two-level NAND. I already told you. See, basically, if you want to represent the SOP, if you want to represent the SOP, the first level you should keep the first level that you have to always keep the AND gates, and then you have to keep the OR gates. Then it is equivalent to basically NAND. It is equivalent to basically NAND. So this is the important point that you always have to keep in your mind. So therefore, simply I can tell you that. So you can say simply it is equivalent to NAND logic circuit. So I have already told you one important point. So two-level AND or logic circuit is equivalent to two-level NAND. These things I have already told you. So therefore, SOP circuits can be easily realized with the help of NAND logic circuit. So therefore, two-level AND or means it is basically sum of products. So therefore, two-level AND or logic circuits is equivalent to two-level NAND. So therefore, two-level AND or logic circuit is equivalent to two-level NAND. So therefore, two-level AND or logic circuit is equivalent to two-level NAND representation. So this is the important thing that you always have to keep in your mind. So two-level AND or logic circuit is equivalent to two-level NAND. So therefore, whatever the SOP, we are going to represent the circuit with the help of AND. For the first level as AND and second level as OR. We can also represent with the help of two-level NAND logic circuit. So therefore, two-level AND or logic circuit is equivalent to two-level NAND. So I already told you AND OR means it is basically equal to NAND logic circuits means SOP, whereas OR AND is called as the basically POS. So these are called as a POS. It is equivalent to NOR level circuits. So these are equal to NOR level circuits means I can tell you that SOP circuits can be easily realized with the help of NAND level circuits, whereas the POS circuits can be easily realized with the help of NOR level circuits. So these are the things that you always have to keep in your mind. So finally I can say that SOP can be easily realized with the help of NAND level circuits, whereas the POS can be easily realized with the help of NOR level circuits. So these things that you always have to keep in your mind. So SOP means sum of products can be easily realized with the help of AND or NAND level circuits, whereas the POS can be easily realized with the help of OR AND or simply NOR level circuits. See, all essential prime implicants are prime implicants, but all prime implicants are not essential prime implicants. I already told you. See, all essential prime implicants are prime implicants, but all prime implicants are not all essential prime implicants. So these are the important points that you always have to keep in your mind. I already told you all essential prime implicants are prime implicants, but all prime implicants are not essential prime implicants. So therefore, all essential prime implicants are prime implicants, but all prime implicants are not essential prime implicants. This is the important point that you always have to keep in your mind. So therefore, all essential prime implicants are prime implicants, but all prime implicants are not essential prime implicants. I already told you essential prime implicants means if you group some of the cells, at least one of them is not matched with any other grouping of cells. So that is called essential prime implicants. Whereas for prime implicants, see, so all the cells can be grouped by any other grouping also. So we can say that always all essential prime implicants are prime implicants, but all prime implicants are not all essential prime implicants. So all essential prime implicants are prime implicants, but all prime implicants are not essential prime implicants. So these are the points that you always have to keep in your mind. See, NAND, NOR, A bar plus B, A bar B, MUX, ROM are always universal gates. I have already told you this important point. I have already told you NAND gate, NOR gate, A bar B, A B bar, A bar plus B, and A plus B bar, and also ROM. All these are called as the universal gates, or one is also called as the read-only memory. So all these are called as the universal gates. So these are the things that you always have to keep in your mind for your lifetime. So therefore simply we can say NAND gate, NOR gate, A bar B, A bar plus B and A plus B bar, and also we can say ROM, MUX and ROM. All these are called as the universal gates. So NAND gate, NOR gate, A bar B, A B bar, A bar plus B, A plus B bar, and also MUX and also ROM. All these are called as the universal gates. So BCD is also called as the 8421 code. So BCD is also called as the 8421. So BCD means binary coded decimal. So each decimal number we are going to represent with the help of 4 binary bits. That is called as the BCD representation, binary coded decimal. So BCD is also called as the 8421 code. So BCD is also called as the 8421 code. So BCD is also called as the 8421 code. See, encoder converts other codes to binary. I will only tell you what is the meaning of encoder. Encoder means it is always going to convert the other number system to the any other number system to the binary number system, whereas the decoder is going to convert the binary number system to any other number system. All these things I already explained. So therefore encoder is always going to convert the any other number system to the binary number system, whereas the decoder is going to convert the binary number system to any other number system. Similarly, I already told you the full adder. So we are going to represent the full adder with the help of 2 half adders plus 1 OR gate. Similarly, we can represent the full subtractor with the help of two half adders plus 1 OR gate. So therefore simply one full adder we can represent with the help of 2 half adders plus 1 OR gate. Similarly, one full subtractor we can represent with the help of 2 half subtractors plus 1 OR gate. So one full adder we can represent with the help of 2 half adders plus 1 OR gate. Similarly, one full subtractor we can represent with the help of 2 half subtractors plus 1 OR gate. So one full adder we can represent with the help of 2 half adders plus 1 OR gate, and one full subtractor we can represent with the help of 2 half subtractors plus 1 OR gate. So one full adder we can represent with the help of 2 half adders plus 1 OR gate, and one full subtractor we can represent with the help of 2 half subtractors plus 1 OR gate. Now we are half adder. So half adder we can represent the half adder with the only 5 number of NOT gates and also 5 number of NOR gates. Similarly, half subtractor we are going to represent with the help of 5 NOT gates and 5 NOR gates. Similarly, full adder we are going to represent with the help of 9 NOT gates and 9 NOR gates. Similarly, full subtractor we are going to represent with the help of 9 number of NOT gates and 9 number of NOR gates. So this is the important point that you always have to keep in your mind. So finally I can say that, so half subtractor, so to build the half subtractor we need minimum 9 NAND gates. Similarly, 5 NOR gates we are going to represent. Similarly, half subtractor we need 5 number of NAND gates and also 5 number of NOR gates. Similarly, full subtractor, full adder, we need 5 number of NAND gates and 9 number of NOR gates. Similarly, for full subtractor we need 9 number of NAND gates and 9 number of NOR gates. So this is the important point that you always have to keep in your mind. So half adder and half subtractor both require 5 for NAND gates and also NOR gates. Similarly, full adder and full subtractor we need 9 number of NAND gates and 9 number of NOR gates. So this is the important thing that you always have to keep in your mind. So these things I already told you whenever I am explaining the half adder and half subtractor and full adder and full subtractor. I am explaining with the diagrams also. In the parallel adder, whenever the propagation delay of the sum is equal to propagation delay of the carry, let me also, which is TPD, then for one complete addition, then I have already told you what is the value of one complete addition. See, one complete addition we are going to get a time which is n minus 1 into the propagation delay of the carry plus maximum of the propagation delay of the carry comma propagation delay of the sum. See, if both are equal means n of maximum is nothing but anything that we are going to get only 1. So n minus 1 plus 1 is equal to n. So n into TPD. So therefore we can say for one complete addition number, the amount of time taken is n into TPD. So the rate of addition is equal to 1 by the time completion for one addition, which is 1 by n into TPD. So these things I have already told you. So rate of addition means the number of complete additions in 1 second, that is called the rate of addition. So rate of addition means the number of complete additions in 1 second, it is called as the rate of addition. So the rate of addition means the number of complete additions that are going to take place in 1 second is called as the rate of addition. So rate of addition means the number of complete additions that are taking place in 1 second is called as the rate of addition. And this is the very important point that you always have to keep in your mind. So rate of addition means the number of complete additions that are taking place in 1 second is called as the rate of addition. So rate of addition means the number of complete additions taking place in 1 second is called as the rate of addition. So for one complete addition we are going to get n into TPD. This is the special case which is only when TPD sum is equal to TPD carry. But the general format I have already told you, which is for one complete addition the amount of time taken is which is equal to n minus 1 into TPD carry plus maximum value of TPD carry comma TPD sum. So therefore if you want the time, the rate of addition which is 1 by the time taken for one complete addition which is 1 by n minus 1 into TPD carry plus maximum value of TPD carry comma TPD sum. So this is a special case of this one. So if you keep these conditions we are going to get this one. See, in ones and twos complement representation, when extending the number of bits for representation, just copy MSB, that's it. I already told you, in ones and twos complementation representation, when extending the number of bits for representation, just copy the MSB, that's it. So basically, in the ones and twos complementation representation, I already told you, whenever you are extending the number of bits, so whatever the MSB bit, just copy it for all the remaining more bits, you are going to get the same representation. So therefore, in ones and twos complement representation, when extending the number of bits for representation, just copy MSB, that's it. So in the ones and twos complement representation, when extending the number of bits for representation, just copy MSB, that's it. So in ones and twos complement representation, when extending the number of bits for representation, just copy MSB, that's it. So therefore, in ones and twos complementation representation, if you are extending the number of bits for representation, then just copy MSB, that's it. So you can say clearly here, suppose plus 13 is there, if I am going to write here 0, 1, 1, 0, 1 in terms of one complement, in terms of one complement representation, which is 0, 1, 1, 0, 1 using 5 bits. So if you want to represent with the help of using 8 bits means here MSB is 0, so extend for the remaining bits 0. So the remaining 3 bits we are going to represent with this MSB, it is again 0. Similarly, suppose if I want to represent using 8 bit, then what is plus 13 means in terms of minus 13 it is nothing but 1, 0, 0, 1, 0. But if you want to extend it in terms of 8 bits, it is simply you have to go for the remaining thing. I say clearly, all these are the one complement representation. A small example here, I want to explain this concept in terms of one complement representation. So you can say clearly plus 13. Suppose in terms of 5 bits, I can write like this 0, 1, 1, 0, 1 in terms of 5 bits. Suppose I want to write in terms of 5 bits for minus 13. So minus 13 means just to the complement of this one. So 1, 0, 0, 1, 0 in terms of one complement representation. So this is plus 13 and minus 13 in terms of 5 bits. But if I want to write the plus 13 in terms of 8 bits, so this is the MSB. So the remaining bits you have to extend this one. So you can see clearly the remaining bits, 3 bits you have to extend the MSB, which is 0 here. So 0, 0, 0. Remaining thing is same here. So this is called the plus 13 in terms of 8 bit. Similarly, I want to represent the minus 13 in terms of 8 bit. So this is the MSB is 1. The remaining 3 bits are also we have to see, we have to keep the same value as 1. So 1, 1, 1. And remaining thing is same. So therefore, what I am trying to tell you, in ones and twos complement representation, when you extend the number of bits for representation, just copy the MSB, that's it. So plus 13 in terms of 5 bits and plus 13 in the terms of 8 bits. So whatever the MSB, same thing I have extended, just copied it and pasted it here. Same thing you have to extend. Whereas the minus 13 in terms of 5 bits and minus 13 in terms of 8 bits. The remaining 3 bits also we have to keep the same value of MSB, just copy and paste the remaining bits also. So this is the concept that you always have to keep in your mind. So in ones and twos complement representation, when extending the number of bits for representation, just copy the MSB bit, that's it. In ones and twos complementation. So 8 cells called as the octet, 4 cells called as the chord, 2 cells called as pair, always map from high to low. See, if you are grouping the 8 cells, it is called as the octave. If you are grouping the 4 cells, it is called as the quadrant. If you are grouping the 2 cells, it is called as the pair. So always try to map from high to low. So try to map from high cells to the low cells in the power of 2 to the power of n. So if you group the 2 to the power of n, then n variables are related. I already told you, if you are grouping the cells in the order of 2 to the power of n or n, anything is same, then n variables are going to get redundant. So 8 cells if you group, it is called as the octet. If you group the 4 cells, it is called as the quadrant. If you group the 2 cells, it is called as a pair. So always try to map from high to low. So multiplexer is also known as many to one circuit or data selector. So multiplexer is also called as a many to one circuit or data selector or universal logic circuit or parallel to serial data converter. So this is the important point that you always have to keep in your mind. So multiplexer is also called as a many to one circuit or data selector or universal logic circuit, or it is also called as a parallel to serial data converter. So I already told you basically the main function of multiplexer. So multiplexer is also called as the many to one circuit or data selector or universal logic circuit or parallel to serial data converter. So multiplexer is also called as the many to one circuit or data selector or universal logic circuit or parallel to serial data converter. So basically it is a because it has more number of inputs with one or two. So it is called as a many to one circuit or data selector, means one time one data can be gone to the output. So therefore it is called as the data selector or universal logic circuit, because once is always the universal logic circuit, or it is also called as the parallel to serial data converter. So finally multiplexer is also called as the many to one circuit or data selector circuit, or it is also called as the universal logic gate, or it is also called as the parallel to serial data converter. So these are the different names for the multiplexer. So multiplexer is also known as the many to one circuit or data selector or universal logic circuit or parallel to serial data converter. See, logic gates like AND or NOT require only one mux 2x1 to implement them. I already told you, if you want to implement the logic gates like AND gate, OR gate, NOT gate, then we require only one mux, which is 2x1 to implement them. These things I have already shown you when I am going to represent the mux as a universal gate. So if you want to build the logic gates like basic gates like NOT gate, OR gate and AND gate, then we need only one 2x1 mux to implement them. Whereas the logic gates like NAND gate, NOR gate, XOR gate, XNOR gate requires two 2x1 mux to implement them when complements are not available. So basically in the NAND gate, NOR gate, XOR gate, XNOR gate, they are going to even require the complement of the signals. So if you want to represent the complement, again you need one more 2x1 mux. So therefore simply we can say that the logic gates like NAND gate, NOR gate, XOR gate and XNOR gate requires two 2x1 muxes to implement them when complements are not available. Suppose if complements are available, means they also require only one 2x1 mux. Suppose if the complements are not available, means they require two 2x1 muxes. So this is the important point that you always have to keep in your mind. So logic gates like NAND gate, NOR gate, XOR gate and XNOR gate, they require two 2x1 muxes whenever the implements are not available. Whenever the complements are not available, if complements are available, then they require only one 2x1 mux to implement them also. DMUX and decoder internal diagram is perfectly same. I already told you decoder and DMUX both are same, just we have interchanged the enable and the selector lines. That's it. Then see, basically for DMUX we have interchanged the input and also select lines, then we are going to get the decoder. So we can say DMUX and decoder internal diagram is perfectly same. They are identical, they are one only. Just for the DMUX we have interchanged the input and also the select lines, then we got the decoder. So DMUX and decoder internal diagram is perfectly same. And the general representation of any mux is to the power of n cross 1. So general representation of any mux is to the power of n cross 1, where n is the number of control inputs or select lines. I already told you here the general representation of any mux is to the power of n cross 1, means the number of inputs are to the power of n and the output is only 1 and the number of select lines are n. So it is called as basically the general representation of any mux is to the power of n cross 1. The to the power of n is the number of input lines and 1 is the output line and n is the number of control inputs or select lines. So these are the important things that you always have to keep in your mind. So general representation of any mux is to the power of n cross 1, where n is the number of control inputs, or we can say number of select lines. So general representation of any mux is to the power of n cross 1. The to the power of n is the number of input lines and 1 is the output line and n is the number of control inputs or select lines. Whereas general representation of any dmx is 1 cross to the power of n. Whereas general representation of any dmx is 1 cross to the power of n. 1 is the number of input lines and to the power of n is the number of output lines and n are called the control inputs. Whereas the general representation of any decoder is basically n cross to the power of n. N cross to the power of n. N is called the number of input lines and to the power of n is the number of output lines and there will be one enable input. See, what is the meaning of tri-state buffer? This is basically a buffer. So this is the buffer circuit. You can see this is the input is A and this is the output is Y and this is the enable input E. So you can see, suppose whenever the enable input is equal to 0, whatever the output is always high impedance state, and whenever the whenever the enable is equal to 1, so it is activated whatever the output is equal to input. So therefore you can see A can have 0, 1 and high impedance state. So these are the three states possible for output Y. So this is called as the tri-state buffer. So Y can have 0, 1 or high impedance state. So these are the three states possible for the output of this tri-state buffer. So it is called the tri-state because Y is having three states. So it is called as a tri-state buffer. So whenever E is equal to 0, then always output will be always in the high impedance state. Whenever the E is equal to 1, then always Y is equal to A. So Y can have either 0, it can have either 1 or high impedance state. So these are the three states are possible for the circuit. So it is called as the tri-state buffer. So Y can have either 0, 1 or high impedance state. So these are the three, you can say three states, which are the three states are possible. So because of this reason it is called as a tri-state buffer. So as the output Y can have three states, whether it can be 0, whether it can be 1 or whether it can be high impedance state. So because of this reason it is called as a tri-state buffer. So if you see the circuit diagram, it is the input is A and this is E is called as the enable input and Y is called as the output. So whenever the enable input is equal to 0, then Y is always in the high impedance state, and whenever the enable input is equal to 1, so whatever the output should be always equal to A. So Y can be either 0, it can be either 1 or it can be either high impedance state. So it has three states. So that is the reason this circuit is called as a tri-state buffer. So in a BCD, we want to do any operations by using 1's complement and 2's complement strategies. So in BCD, we won't do any operations by using the 1's complement and 2's complement strategies. So in the BCD, we never do any operations based on 1's complement or 2's complement strategies. So in the BCD, we never apply 1's and 2's complement in order to do the addition or subtraction operation. So therefore, we don't do any operations in BCD. We never do any operations. We never do any operations by using the 1's complement or 2's complement strategies. So this is a very important point. In BCD binary code decimal, so each and every decimal number we are going to represent with the help of 4-bit binary. So therefore simply we can say that in BCD we won't do any operations by using the 1's complement or 2's complement strategies. So in the BCD we won't do any operations by using the either 1's complement or 2's complement strategies. So in the BCD we won't do any operations by using 1's complement or 2's complement strategies. So I have already told you XS3 code is nothing but BCD code plus 0011. So XS3 code is nothing but BCD code plus 0011. So if you add 3, if you add plus 3, if you add plus 3 to each and every BCD code, then whatever the code is called as the XS3 code. So 0011 is 3. So if you add plus 3 for each and every binary code with decimal, then you are going to add a XS3 code. So therefore XS3 code is equal to BCD code plus 0011. So therefore simply I can say that XS3 code is nothing but BCD code plus 0011. So therefore XS3 code is equal to BCD code plus 0011. So for the each and every BCD code, if you add 0011, then it is called as the XS3 code. So XS3 code is nothing but BCD code plus 0011. So XS3 code means BCD code plus 0011. So if you add 3 for each and every BCD code, then whatever the resultant is called as the XS3 code. So XS3 code means it is basically you have to add 3 to the each and every. So now 2421, 2421, 3321, 4311, 5211, 642 minus 3, and all these are self-complementing and weighted codes, but they sum up to 9. You can see if you add all these things, 2 plus 4 is 4, 2 plus 4 is 6, 6 plus 2 is 8, 8 plus 1 is 9. Similarly 3 plus 3 is 6, 6 plus 2 is 8, 8 plus 1 is equal to 9. Similarly 4 plus 3 is 7, 7 plus 1 is equal to 8, 8 plus 1 is equal to 9. Similarly 5 plus 2 is 7. 7 plus 1 is equal to 8. 8 plus 1 is equal to 9. 6 plus 4 is equal to 10. 10 plus 2 is equal to 12. 12 minus 3 is equal to 9. So all these are called as a self-complementing and weighted codes, and they sum up to 9. So these are called as the self-complementing and also weighted codes, and they sum up to basically 9. So if you add all these things, we are going to get the 9. So these are called as the self-complementing and also the weighted codes. So all these are called as the self-complementing and also weighted codes, and they sum up to basically 9. So therefore 2 4 2 1, 3 3 2 1, 4 3 1 1, 5 2 1 1 and 6 4 2 minus 3, all these are called as self-complementing and the weighted codes, and they sum up to 9. So all these are called as self-complementing and weighted codes, and they sum up to 9. Setup time is the minimum time to keep the data ready before active edge of clock coming. So setup time is the minimum time to keep the data ready before active edge of clock coming. So therefore, setup time is the minimum time that you have to keep the data ready before active edge of clock coming. So therefore, here we can say that it is basically, it's a simple case. See, suppose if you are going to go to railway station, then you have to go sometime before the train arrives. So you have to go sometime before the train arrives. So that is called as a setup time. Yes, you have to go to the railway station to catch the train. So before the train comes, you have to go somewhat early. Then that is called as the time which you came early before the train arrives. It is called as setup time. So setup time is the minimum time to keep the data ready before active edge of clock coming. So therefore we can say setup time is the minimum time to keep the data ready before the active edge of clock coming. So therefore we can say setup time is the minimum time to keep the data ready before the active edge of clock is coming. So therefore setup time is the minimum time to keep the data ready before the active edge of clock is coming. So this is the important time that you always have to keep in your mind. So setup time is the minimum time to keep the setup time is the minimum time to keep the data ready before the active edge of clock incoming. So setup time is the minimum time you have to keep the data ready before the active edge of clock is coming. So setup time is the minimum time to keep the data ready before the active edge of clock coming. Similarly, hold time is the minimum time to keep the same data at flip-flop input after the applying clock to store the data. So after the coming of the clock signal, you have to keep the same input for certain amount of time in order to keep the data to store into the flip-flop. That is called as the hold time. So therefore hold time is the minimum time to keep the same data at the flip-flop input after applying the clock to store the data. So we can say setup time means it is a time for which the data should come earlier, so before the clocking of pulse. And hold time is the, you have to keep the same data at that flip-flop input you have to keep for a certain amount of time. So therefore this remote can store inside the flip-flop. So therefore we can say setup time is the minimum time to keep the data ready before the active edge of clock coming, and hold time is the minimum time to keep the same data at the flip-flop input after applying the clock to store the data. So therefore these are things here. Setup time is, I already told you, so you are going to railway station, so you have to go somewhat earlier time when come to the train comes. It is called setup time, and after that train comes, you are going to sit in the train. So train should you have to sit in a train for a certain amount of time before the train goes away. So because you have to go and sit in the train, so the data should go and enter into the flip-flop, so it is taking certain time. So that is called as the hold time. So setup time is the minimum time to keep the data ready before the active edge of clock coming. Similarly, hold time is the minimum time to keep the same data at flip-flop input after applying the clock to store the data. So setup time is the minimum time to keep the data ready before the active edge of clock coming, and hold time is the minimum time to keep the same data at flip-flop input after applying clock to store the data. If setup time and hold time is not meeting, then output is in the metastable state, means output can be predicted perfectly. So if setup time and hold time is not meeting the conditions, then output is in the metastable state, means output can be predicted perfectly. Suppose if you are not keeping the input as per these times, if you are not keeping the input data for a flip-flop as per these times, means whatever the output, it is called as a metastable state, means you can't perfectly predict the output. So therefore we can say that if setup time and the hold time is not meeting properly, then whatever the output is in the metastable state, means the output can be predicted perfectly. So you don't know what is the actual output because you can't predict them because you are not satisfying the minimum conditions of the setup time and the hold up time. So therefore, setup time is the minimum time to keep the data ready before the active edge of clock coming, and hold time is the minimum time to keep the same data the flip-flop input after applying the clock to store the data. If these two times are not meeting as per the conditions, then we can say that suppose if you are going to give the input, if it is not meeting these conditions, then definitely output is in the metastable state, means output can't be predicted perfectly. So always I want you to know what are the clock time should be always getting or equal to the propagation delay of the flip-flop plus setup time. So what is the clock frequency? The clock frequency is equal to 1 by clock time. So clock frequency is always less than or equal to 1 by the propagation delay of the flip-flop plus setup time. So therefore this is the formula. The maximum clock frequency is equal to 1 by the propagation delay of the flip-flop plus setup time. So this is the important thing that you always have to keep in your mind. See, clock time. The clock time should be always greater than or equal to the propagation delay of the flip-flop plus setup time. So therefore f clock is equal to 1 by t clock. So f clock is always less than or equal to 1 by t PD of the propagation delay of the flip-flop plus setup time. So maximum clock frequency is equal to 1 by propagation delay of the flip-flop plus setup time. So if we do the relation, we are going to get this. Maximum clock frequency is equal to 1 by propagation delay of the flip-flop plus setup time. See, here there will be some extra factor which is called the combination delay whenever if any combination circuit is present between them. So then the clock frequency should be always getting equal to the propagation delay of the flip-flop plus some the combination delay plus the setup time. So if any combination circuit is present between them, you have to use this factor also, these term also. Otherwise, you have to use only these two terms. If suppose there is any combination circuit is present between them, so you have to use this extra term also. So clock frequency should be always getting equal to the propagation delay of the flip-flop plus the time for the some combination circuit delay plus the setup time. So if any combination circuit is present between them, so you have to use this term also. So this is the overall condition. Otherwise, you have to take only this first term and the last term. So these are the important things that you always have to keep in your mind. So for general case, we can say if any combination circuit is present, then the clock time should be always greater than or equal to the propagation delay of the flip-flop plus for combination circuit delay plus setup time. So if any combination circuit is present in between them. So I already told you this is called as this is basically registers. So this is basically all the flip-flops. So therefore now I already told you this the clock is given to only this one and the output of one is given as input to the clock for the other and the output of one is given as the clock for the other. So like this if you do this one, so this is basically called as the we can say ripple counters. So ripple counters means asynchronous circuits, means we are going to give clock to only one circuit, one flip-flop, and for the other flip-flops, output of one flip-flop is given as the clock for the triggering for the other circuits. So this is called as the ripple counters or asynchronous. So now you can see here, this is called serial input and this is called the serial output. So basically, serial input, basically what I am trying to tell you is very simple. In this case, we are going to give clock for each and every one is same. So for each and every one, these are not the counters. These are basically, we can say data shifting. We are data shifting from right to left or left to right that we are doing. In this case now we are going to give clock for each and every one same instant. So we can say these are called as synchronous. And we are shifting the data from left to right or right to left. So you can say for all these flip-flops we are going to give the same clock at the same instant. So we can say this is said to be synchronous clock. So now this is called serial input and this is called serial output. For serial input we need n number of clock pulses to store the n number of bit here, and for serial output we need n minus 1 number of clock pulses to take the n number of bit. Similarly, this is called serial input and parallel output. Serial input means we need n number of clock pulses to store the n number of bit in these registers, and whereas for parallel output we require only 0 number of clock pulses because they are directly available, and this is called as a parallel input and the serial output. So for parallel input we need only one clock pulse to store the data, and for serial output we need n minus number of clock pulses to take this n bit input. Similarly, this is called the parallel input and parallel output. So for parallel input we need only one number of clock pulses to store the n bit data, and for parallel output we require only 0 number of clock pulses to take this n bit data. So this is the point that you always have to keep in your mind. So serial input, serial output, parallel output, parallel input, serial output, and parallel input and parallel output. I already told you serial input means n number of clock pulses, serial output means n minus 1 number of clock pulses, parallel input means 1 number of clock pulses, and parallel output means 0 number of clock pulses. I already told you. So basically this clock pulses indicates this number of n number of bits. It requires the amount of storage. So finally I can say for serial input n number of clock pulses are required to store the n number of bits. The serial output requires n minus 1 number of clock pulses to take out the n number of bit. Whereas for parallel output we require 0 number of clock pulses to take the n number of bits, whereas parallel input requires 1 number of clock pulses to store the n bit data into this registers. All these things I have already told you. See, counters I have already told you, these are called the cascading of flip-flops. So if you cascade the flip-flop one after another, so whatever that is called as the cascading of flip-flops. So if you do the connection of flip-flops one after another, it is called as the cascading. This output of one is given as the input of other, it is called as the cascading of flip-flops. So you can see clearly, so counters means these are the cascading of flip-flops. So for one flip-flop, you can have either 0, 1 state, means 2 states are possible. So for one flip-flop, you can have either 2 states, either 0 or 1. Similarly, for 2 flip-flops, we are going to get 0, 0, 0, 1, 1, 0, 1, 1. So 4 states are possible. For n flip-flops, we are going to get to the power of n, we can say maximum possible states. So I already told you, for one flip-flop, you can have 0, 1, means 2 states. For 2 flip-flop, we are going to get 4 states. For 3 flip-flop, we are going to get 8 states. So similarly, for n flip-flop, we are going to get to the power of n states. Maximum to the power of n maximum possible states. So listen carefully. For one flip-flop, we are going to get 2 states because they can represent the 2 data. Similarly, for 2 flip-flops, we are going to have 4 combinations, means 4 states. And similarly, for 3 flip-flops, we are going to get here 8 combinations, means 8 states. Similarly, for n flip-flop, we are going to get to the power of n maximum possible states. Suppose small m is the number of flip-flops used in the counter, then capital M is called as the number of states used in the counter or mod number or modulus count. So always n is always less than or equal to the power of n. So therefore, if you do that, if you apply the base 2 on both sides, log base 2 on both sides, you are going to get small m greater or equal to log n base 2. These things I have already told you. So therefore, always capital is always less than or equal to the power of n, because small m is called the number of flip-flops and to the power of n is maximum number of states are possible with the help of that number of flip-flops. So n is small n is called the number of flip-flops used in the counter and capital N is called the number of states used in the counter or mod number or modulus count. So out of to the power of n, only capital N states are used. So larger number of states possible at to the power of small m, whereas only capital number of states are used. So therefore, capital is always less than or equal to the power of n. Small n is called the number of flip-flops used in the counter and capital is called the number of states which are used in the counter. It is also called as the mod count or the modulus count. So mod count means the number of states, unique states which are used. So the capital is always less than or equal to the power of small n. So if you apply the log base 2 on both sides, we are going to get small n greater than or equal to log capital base 2. So this is going to give you number of flip-flops required to implement this many number of states. So this is the important thing that you always have to keep in your mind. So small n should be always greater than or equal to log n base 2, and small n is called the number of flip-flops in the counter to implement this number of states. N is the number of states. So this is the important point that you always have to keep in your mind. So counters are basically, we can say it is a cascading of flip-flops. So for one flip-flop, we can have either 0, 1 state, means 2 states are possible. For 2 flip-flops, we can get 4 states. For 3 flip-flops, we can get maximum 8 states. Similarly, for n flip-flops, we can get maximum to the power of small n states. But out of this, we can't use each and everything. We can use only some number of states. So let me assume that is called the capital N. So capital N is nothing but some number of states only we are using out of total to the power of n. So capital should be always less than or equal to the power of n. So if you apply the log base 2 on both sides, we are going to get small n greater than or equal to log capital N base 2. So n is going to give you, small n is going to give you total number of flip-flops which are used in the counter, and capital N is going to tell you the number of states which are used in the counter. It is also called the mod count or the modulus count. We are going to discuss about the, suppose there is a modern counter like this. So modern counter means it is going to have n unique states. These things I have already told you. Suppose the clock frequency is f. then what is the output frequency? So MSB bit, the output frequency we need to figure out, which is clock frequency by mod n. So listen carefully. So whatever this mod n counter, keep this value divided by n here. So therefore we can say if the clock has a frequency of f, so the MSB of this counter is having a frequency which is f by n, where n is called as the mod of this counter. The mod means the number of unique states of this counter. Similarly, suppose if you are going to do a series combination, or you can say cascade combination of the mod m counter and mod n counter, if you are going to give a clock of frequency f, then here the output of this first mod m counter is f by n, and here it is going to act like now input to this mod n counter. So overall output is f by m by n is nothing but f by m into n. So if the input frequency, the clock has input frequency of f, the output frequency is nothing but f by mn. So it is going to act like a mod which is m into n. So this is equivalent to mod m into n counter. So we can say it is going to act like a counter with that which is having a mod number of m into n. So therefore if the clock has a frequency of f, then the output frequency is equal to f by mod which is m into n. So mod number is m into n. So the number of states is equal to m into n, or you can say the number of unique states in this counter is basically m into n. So these are the things that you always have to keep in your mind. So we can say in this series combination, the first circuit has only a mod m counter, it has only mod m unique states, whereas this one it has only n unique states. So if you do a cascade connection of this, it is going to have the number of unique states are m into n. So this is a very important point that you always have to keep in your mind. So now listen carefully, there is a up counter. Up counter means here it is going to read like 0, 1, 2, 3, 4, 5, 6, 7 and then comes to 0. Because we are going to assume it has only 3 bits. So for 3 bits it can read only from 0 to 7, again it is going to read back the 0. So sequentially means it is in a loop format. So 0, 1, 2, 3, 4, 5, 6, 7 again 0. So this loop is going to get repeated. It is called as the up counter. Whereas if you want the down counter means 0, initial state we are going to get 0, 7, 6, 5, 4, 3, 2, 1, 0, 7, 6, 5, 4, 3, 2, 1. So we can say it is in a sequence manner. So it is in a sequence of manner from up to down. So it is called as a down counter. So this is basically for generally 3 bits only. Suppose if you want any sequence, if you want any random sequence to generate, like example 0, 3, 6, 4, 1, 2, 0. Again 3, 6, 4, 1, 2, 0. So you can see clearly the numbers are not in the either decreasing manner or increasing manner, but they are in the random fashion. So this is called as any sequence or random sequence. So listen carefully. First 3 are designed by synchronous counters, but first 2 only are designed by asynchronous counter. So listen carefully. If you are going to use a synchronous counter, then any of these 3 things that you can implement. Suppose if you are going to use the synchronous counter, suppose if you are going to use the synchronous counter, then you can build any of these 3. So you can build all these 3 with the help of you can build all these 3 with the help of synchronous counter. So you can build all these 3 with the help of synchronous counter. So we can either go up counter, either we can go down counter, or we can even go for any sequence generation. So first 3 are designed by synchronous counter, whereas the first 2 only are designed by asynchronous counter, but not the random sequence. So with the help of synchronous counter, we can design all these sequence. Either it can be up counter, either it can be down counter, either it can be any random sequence. Whereas in asynchronous counter, we can only generate only the up counter or down counter, but not the any sequence. We can say any random sequence, because I have already told you synchronous counters means all the flip-flops are being given the same clock and all are going to get the sequence at the same instant. Whereas for this one, asynchronous counter, Here, output of one flip-flop is given as a clock triggering to the other flip-flop. So these are said to be asynchronous counter. So with the help of synchronous counter, we can design the up counter, down counter, or any random sequence. Whereas with the help of asynchronous counter, we can basically build or generate only the up counter or down counter, but not any random sequence. Suppose if you want to find what is the number of flip-flops required, it is equal to t clock by the propagation delay. So always you have to remember this important formula. See, t clock is equal to n into the propagation delay of the flip-flop. So t clock is equal to n into the propagation delay of the flip-flop. This is the case for the ripple counter. This is the case for the ripple counter. This is the case for the ripple counter. So therefore, t clock is always greater than or equal to n into TPD ff. So the t clock is always greater than or equal to the number of flip-flops times the propagation delay of each flip-flop. But we are going to assume all the flip-flops are the same propagation delay. So therefore, we can easily assume like the t clock is nearly equal to, but actually it is always greater than or equal to n into TPD. So therefore now the number of flip-flops required is equal to t clock by TPD. So whatever this value, always try to take the integer value only, because always we need the number of flip-flops, the integer value. So you don't want a fraction value. So you always need a integer value. So you have to take always a integer value out of these things. So these are the important things that you always have to keep in your mind. So now the applications of counter. So what are the applications of counter? You can see clearly. So now we discuss about the applications of counter. See, to count the number of clock pulses applied. So counters are going to count the number of pulses which are going to apply to a counter. So basically this counter is going to count the number of clock pulses that is going to given to the counter. So basically we can say to count the number of clock pulses applied. So for a counter, if you are going to give the clock pulse, it is going to tell you how many number of clock pulses have been given. So it is going to indicate with the help of this counter number. So we can say with the help of counter, we can count the number of clock pulses applied, and it is also act like a frequency divider. And what I told you, the output frequency of a modern counter is, if input has a clock frequency of f, then the output or the MSB bit has a frequency which is f by n, because mod is the n number. So it is going to act like a frequency divider, means we are dividing the frequency. For even frequency measurements also we are going to go for the applications of counter. And also we use these counters in the timers, and also in the distance or range measurement. It is also used in the ADC, analog digital converter, and it also used in some of the control circuits. So we can say simply these are some of the important applications of the counter. So basically these are used to count the number of clock pulses which are applied. It is also going to act like a frequency divider, and it is also going to act like a for frequency measurement, and also it is used in the timers. It is also used for the distance or range measurement. It is also used in the ADC, and also it is used in the control circuits. So these are the important things that you always have to keep in your mind. So these are some of the applications of the counters. So we can say to count the number of clock pulses applied. It is also used as the frequency divider, and for even frequency measurements. It is also used in the timers. It is also used as the distance or range measurement. It is also used for the ADCs and also control circuits. So finally I can say these are some of the important applications of the counters. So we can say very important point, which is to count the number of clock pulses applied. So it is going to count the number of clock pulses which are applied to this counter. It is also going to act like a frequency divider, because it is going to divide the clock frequency. For frequency measurements also we are going to use this one. It is used in the timers, and also used for the distance or range measurement. It is also used in the ADC, and it is also used in the control circuits. Basically, negative edge trigger. So if you give a negative edge trigger, suppose if you are going to give a negative edge trigger and a Q as a clock. So if you are going to give Q as a clock, then it is going to act like a up counter. So this is a very important point. Suppose if you are going to, basically this is all the things for the negative edge, and we can say this is for the ripple counters. So what are this concept is always for the ripple counters. Suppose if you are going to apply negative edge trigger and Q as a clock, it is going to act like a up counter. If you are going to give a positive trigger, whereas the Q bar is a clock, it is going to act like up counter. If you are going to give positive trigger and a Q as a clock, it is going to act like down counter. If you are going to give negative trigger with the Q bar as a clock, it is going to act like down counter. So these are the important things that you always have to keep in your mind. So always you have to keep J is equal to K is equal to 1 means that in the toggling condition or reset condition, then only we are going to get this. It is going to act like a counter. See, this concept is only for the ripple counters. So what it means, or simply we can call it as a asynchronous counters or the ripple counters, because here output of one flip flop is going to trigger again as a clock for the other flip flop. So because of this reason only it is called as the asynchronous counter or the ripple counter. So now this is a very important point that you always have to keep in your mind. So for negative trigger with a Q as a clock, it is going to act as up counter. And for a positive trigger, if Q bar is a clock, it is going to act as up counter. For positive trigger, Q as a clock, it is going to act as down counter. And for negative trigger with a Q bar as a clock, it is going to act as up counter. So this is the important things that you always have to keep in your mind. So now we will discuss something more about this one. You have to remember this table always for your lifetime in the deep digital electronics. So this is the triggering, and this is the clock, and this is the counter. So basically always you have to keep for JK flip flops J is equal to 1 and K is equal to 1. It is always in the reset condition or the toggling condition. So at this condition, so this concept is only for the ripple counters or asynchronous counters only. So easy to remember is minus negative triggering, positive triggering and negative triggering. So this is a Q as a clock, Q bar as a clock, Q as a clock, and Q bar as a clock. So this is up counter, down counter, and down counter. So this table that you always have to keep in your mind. So this is the triggering, and this is the clock, and this is the counter. So negative trigger, positive trigger, negative trigger. Q as a clock, Q bar as a clock, Q as a clock, and Q bar as a clock. So we are going to get up counter, down counter, and down counter. So if you remember this table, it is very much easier to solve any of the questions that are going to be given in the E examination. So negative trigger, positive trigger, negative trigger. Q as a clock, Q bar as a clock, Q as a clock, Q bar as a clock. Up counter, down counter. So these things that you always have to keep in your mind. Clear means output is equal to 0 irrespective of input. I already told you, if you are basically activating the clear, so if you are basically activating the clear means output is equal to 0 irrespective of the input. So we can say no matter whatever the past output, so whenever the clear is activated, always output is equal to 0 irrespective of the input. And preset means output is equal to 1 irrespective of input. So if you are activating the clear means always output is equal to 0 irrespective of the input. And if you are presetting, see, if you are making the preset as activate, then always output is equal to 1 irrespective of the input. So these points that you always have to keep in your mind for all your lifetime. So we can say clearly that here I have already told you. So whenever you are activating the clear input, so basically if you are activating the clear input, by default it indicates that. So if you are activating the clear input means always output is equal to 0 irrespective of the input. Similarly, if you are activating the preset input means always output is equal to 1 irrespective of the input. So therefore clear makes output is equal to 0 irrespective of input. Preset makes output is equal to 1 irrespective of input. So if you are activating the clear input, then always irrespective of the input, output is always equal to 0. And if you are presetting that, if you are activating the preset means always output is equal to 1 irrespective of the input. So these both are used in order to use only few states in the given range. I have already told you we are basically using this either clear or either preset. So because we can, with the help of this, we can use only few states out of the total states. So I have already told you for small n is equal as the total number of flip flops, then 2 to the power of n is equal as the total number of states possible with this n flip flop. So out of this we can use only some of them with the help of this either clear input or preset input. So therefore these both are used in order to use only few states in the given range. So basically we can say with the help of this one, so with the help of this one, with the help of this clear input and preset input, we can use only few states out of the total maximum possible states. So these both are used in order to use only few states in the given range out of the total possible states. So these both are very helpful in order to use only few states out of the total number of possible or maximum states. So these both are used in order to use only few states in the given maximum possible range. So now let me give you some summary for the ripple counters. Ripple counters are also called as asynchronous counter because here I already told you output of one flip-flop is given as the clock, output of one flip-flop is given as a triggering for the other flip-flop. So because of this reason only, these are called as the ripple counters. So these are basically called as the ripple counters based on this concept only. So therefore now listen carefully whether it is a synchronous or asynchronous. So first you have to see whether this is a synchronous counter or whether it is a asynchronous counter. You have to see carefully, this is the important point. So this concept is only for both synchronous counters and also asynchronous counters. So first thing is you have to see from the given circuit. By just seeing the circuit, you have to first confirm whether it is a synchronous counter or asynchronous counter. Synchronous counters means for all the flip-flops, clock is given as the triggering for each and every flip-flop. Same clock is given, so all are going to trigger at the same instant. Whereas asynchronous counter means I already told you, see, so one flip-flop output is given as a clock to the other flip-flop, then it is called as a asynchronous counter. So now you have to see whether the clock is a positive trigger or negative trigger. So from seeing the clock, you have to tell me whether it is a positive triggering or negative triggering. So you have to confirm. Then clock has Q or Q bar. So you have to see the next one is whether clock has a Q or Q bar. So which you are going to give, whether Q has a clock or Q bar has a clock, you need to confirm. And then based on this I have already told you. So based on this I have already told you important points. So based on these three, whether triggering, what type of triggering, what type of is a clock. So based on these two things, you can easily confirm. I already told you, see based on this which is as a clock and which is using as a triggering. So based on this we can confirm what type of counter it is. So up or down we can easily count it because I already shown you the table. If any feedback present or not, so we have to see if any feedback is present or not, we have to check. So if there is no feedback means the total number of maximum possible states capital is equal to the power of n, where small n is the total number of flip-flops available. So total maximum possible states is equal to the power of n itself. So capital is called as the number of states appearing. Suppose if there is some feedback means we are using only few states out of the total possible states. So capital is always less than the power of n. Suppose terminating count figure out. So we have to find what is the terminating count, the final count we have to figure out. So then you can say then a terminating count. So you have to check the terminating count I already told you. So clear, it is going to, if you are active in the clear means output is always equal to 0 0 0. If you are active in the preset means always it is 1 1 1. So based on this you have to find the number of unique states. It is going to tell you about the mode of that counter. So all these things I have already explained. So this is some of the important summary of the ripple counter. So therefore first you have to say whether it is synchronous counter or a synchronous counter, and then you have to check whether it is a positive triggering or negative triggering, and then you have to check whether you are giving Q as a clock or Q bar as a clock. Then from both of these, so from both these you can easily confirm what type of counter it is. Up counter or down counter you can easily figure it out. I have already told you this important point. And if any feedback is present or not, you have to see. If there is no feedback, then always total number of states is equal to the power of small n, where small n is the number of flip-flops available and n is the capital number of steps, the number of states appearing. So both are equal. Suppose if there is a feedback means you are using only few states out of the total possible states. So capital is always less than the power of n, where capital is called the number of states appearing. So from this you have to find what is the terminating count you need to figure out. So I have already told you terminating count means the transient state we have to figure out. So then a terminating count transient state, if it is active in the clear means always output is always equal to 0 irrespective of the input. If you are active in the preset means output is always equal to 1 irrespective of the inputs. Then you have to find how many number of unique states except the transient state. You have to find only the unique states or steady state states you have to figure out. It is going to tell you about the mode of the counter. So these things that you always have to keep in your mind. So summary for ripple counter. So first you have to check whether it is a synchronous counter or asynchronous counter. Then you have to check whether it is a positive trigger or negative trigger. And then you have to check Q as a clock or Q as a clock. So based on these two conditions, you can easily confirm whether it's upcounted or uncounted. And if any feedback is present or not, you have to check. If there is no feedback, the total number of states appearing is equal to the power of n, where capital is the number of states appearing and small n is the number of flip-flops. And if there is a feedback, means you are using only less number of states when compared to total number of appearing. So capital is always less than to the power of small n. Small n is equal to the number of flip-flops and capital is equal to the number of states appearing. And now we have to find what is the terminating count. So transient count you have to figure out. So I already told you at the terminating count, always if you are activating the clear means output is always equal to 0 irrespective of the input. If you are activating the preset means output is always equal to 1 irrespective of the input. All these things I already told you.